Okay, let's keep going with this idea. If you're watching these mini lectures in order of the playlist, we just learned that current carrying wires produce magnetic fields. Now we also know that magnetic fields cause forces on current carrying wires. So if I put two wires next to each other, both carrying a current, then not only are each one producing a magnetic field, but the magnetic field that they're producing is causing a force on the other wire. Let's look at that relationship. It's kind of cool. So let's imagine that we have two parallel current carrying wires and they are a distance d apart. Okay? And we know we're gonna take wire 1. We know that wire 1 has a magnetic field that it is producing surrounding it, right? So that magnetic field has wire number 2 in it. Now, if wire number 2 is carrying a current, it has to feel a force due to that magnetic field. Let's flesh this out. Let's flesh this out for a second. We know that the magnetic field produced by wire 1, we just learned that the magnetic field produced by wire 1 is equal to mu naught over 2 pi times the current in wire 1 divided by the distance away from wire 1, wherever we're looking at the magnetic field away from wire 1. Well, that's the location of wire 2. So in this example, the distance from wire 1 is the location of wire 2. So there's a magnetic field of that strength at the location of wire 2. Because wire 2 is carrying a current, wire 2 experiences a force by that magnetic field, so a force by the magnetic field of wire 1, which we know based on our current in a magnetic field relationship in that mini lecture, so go check that one out if it's been a little bit, which is equal to the current in the wire 2 in this case, times the length of that wire times the strength of the magnetic field that wire is running through. And in this case, that magnetic field is from wire 1. So now we're going to put this relationship in to my force relationship. So we end up with the force on 2 by the magnetic field generated from wire 1 is equal to the current of wire 2 times the length of wire 2. And I'm going to plug this in. Mu sub naught over 2 pi times the current wire 1 over the distance between 1 and 2, where d again is that distance between 1 and 2. We don't usually see it in this form, so I'm going to rearrange this. Literally just moving variables around, and the way that we usually see this relationship provided is mu naught over 2 pi, current 1, current 2, all over the distance between 1 and 2 times the length of 2. This is the force on wire 2. The force on wire 2 by a current carrying wire near it by the magnetic field produced by wire 1. Okay, similarly, if I was going to look at the force on 1 by 2, we would look at the length of wire 1 would be important in our relationship. Okay, so this is the magnitude of the force. It's going to be important. All right, that's a relationship we're gonna use. What about the direction? We know forces have a direction. What about the direction of the force that wire 2 experiences from the magnetic field produced by wire 1? Well, that again is just that right-hand rule. And when you do the right-hand rule, we find that the current, when in the same direction the forces are towards each other. So the wires are towards each other. So when the currents are in the same direction, so if I have my two wires, and the currents are both in the same direction, the forces are towards each other. Conversely, when the currents are opposite, the forces are away. So again, my two wires. If current 1 is in this direction, but current 2 is in this direction, oops, use the same colors. The forces they experience are in opposite directions. Okay, so let's do an example problem looking at what happens if I have a horizontal wire horizontal wire with a current going through it, and I want to suspend another wire right below it. How do I do that? What current do I need to put in that lower wire so that it stays suspended in air? All right, we're going to do that in the example problem video. Good job.